Well, now we'll take a look at the pseudocode that you will be implementing to apply Euler's method. So this is the pseudocode, and I've changed it up just because you probably should be used to seeing different variables with differential equations. Notice this time we're trying to get x, and it's a function of t. On the previous video it was y that was a function of x. So this is our initial value problem that we're trying to estimate at a particular time other than time a. So the interval is a to b, and you can see why that's the case. You can see why it starts at a, because that's our initial value, our initial time that we're given, and it'll probably be 0 in most of our examples. And you might guess we're going to try to predict or estimate the value of the function x at time b, using some number of steps to go from a to b. And here's how you'd write the formula using a step size of h. If we knew x of t, then we go one step size beyond that. H could be, 1/10, something like that. Well, we'd go back and say, well, that's x of t plus the step size times f of xt, the slope that we got from that right there. This is x prime of tx. So we'll, and I guess we need to say that h, being the step size, is b minus a over n, and I'll put in parentheses n equals number steps. So if n is equal to 2, you'll have 2 steps. You'll go halfway and then all the way to b. All right, well, the pseudocode looks like this. Basically, you have to know the number of steps, and you have to know what a and b are, and you just define h to be that. b minus a over n. That gives you the step size. And as far as the time goes, our t variable, we're starting it at a. Again, most of the time that'll be 0 for us. And this is, I called it solution. I could have called it x, but I didn't want it to get confused with our other x variables. This is like x at time 0, although technically, this is fine. What we're saving is a bunch of ordered pairs, and we're going to end up plotting those ordered pairs in a way that looks like, something like this. We'll connect the ordered pairs for each step with a line segment. So again, this is only used for plotting purposes at the end. Now we have a for loop. I will use for k, goes from 1 to n. I don't need to start it at 0 because I already know what, by the initial value given to me, I already know the first ordered pair, the 0th ordered pair that's given to us. And then we'll say that x gets the value, this is like the new x, gets the old x plus h times f of tx. That's this formula right here. So this is like saying x at time I plus 1 is x of I plus h times f of t of I, comma, x of I. And then we increment t. The next t is going to move one step size closer to b. Just going to increment it by h. And we save, indexed by k, x. And that's it. Now after that, if you implement this in Mathematica or whatever program you're using, we haven't displayed anything at all. But notice what we have. We know all of the timestamps. the time variable starts at a, and then it goes to a plus h, and then a plus h, and so on. It keeps getting incremented. And solution is the value of the function at each of those points. So we could, in Mathematica, I'm going to show you how you could, to plot a list of points. And I'm going to plot list values, LST I called it, equals 2, 4, 6, 8. I just made this up. This has nothing to do with this program. I just want to show you how to plot points. That list, 2, 4, 6, 8. One way you could do it is the discrete plot command in Mathematica, and you take LST, and you put a letter there, it doesn't have to be K, comma, essentially this makes K go from 1 to 4, like this, 1, 2, 3, 4, and it'll plot each of those points. So that comes out of list. Oops, I guess I capitalized list there where I shouldn't have. So essentially this would plot like 1, 2, 2, 4, 3, 6, 4, 8, because K goes from 1 to 4. Another method, and you could experiment with that to make it print out what you want it to print out. You can do, see, I need a little extra room. I'm going to come way down here and do graphics. That's the word graphics with a capital G, and then line. And in line is a function that takes a list, like, and maybe I'll pick the same numbers up there if I have enough room. 1, 2, 2, 4, 3, 6, 4, 8. So this is a nice command. You can put whatever ordered pairs you want in there, and it'll come from what you determined in your program. And this will just connect with a line segment, this point to this point to this point to that point. And I think I have one final comment, unrelated to the pseudocode. If you wanted to improve this method, obviously I think the best way is to make your step size h smaller and smaller. But you could also, instead of doing what we did right here, well, we're not going to do this in our homework, but you could go, you know, this is a Taylor series method, so we could go out one term beyond the linear term, we could go out one more term. Actually, you could go out to a third term where you get 1 over 3 factorial and so on. This probably doesn't gain you a whole lot. It's probably better to use a completely different method. This would be an improvement. And one downside on this is that you have to be able to compute the derivative of the function f you're given. When you do it in this method, you don't need to take the derivative of the function f. The function f is a derivative given to you. So again, we will not worry about this in the homework at all. We will learn about another method in a future video.